put up this limited space antenna or this type of antenna, this is what I can expect to happen. This is the compromise I have to make in order for this to work. So there is one other thing that we want to look at here, and this is another equation, power. I'm at some distance away. So you've got your transmitter going, and I am X hundred miles, X thousand miles, kilometers away. What kind of power can I expect to get from you? And of course, we want to maximize that power. Everybody's fighting noise. You're fighting receiver noise, you're fighting static on the radio. You want your signal to be strong enough to come through. And this is, again, there's a way of looking at these. This takes the two fields and puts them together, and it says, okay, let's take basically a form of a product of these two things, and we add them up over a big surface. Like you say, we'll draw a line or a big sphere around our radio station that's 10 miles away or something like that. And we're going to say, let's measure all of that energy, all of that power that's crossing that sphere, flying out into space. And we're going to add that all up. And that will tell us how well our antenna is radiating. And this is done. But notice what's going to happen here. I'm going to just cut to the chase. There's a few terms here which are interesting, but here's the gorilla right here. Notice again, this is what's going to increase the power. These are all constants. This is, like the frequency you're on. This is things to do with magnetic fields and things like that. And obviously 12 pi is, a constant. But right here, the more current and the more wire you have, the more power you're going to deliver at some receiver point away, okay? That's what's going to radiate. So we want to take this now and say, all right, what can we do with this? What we can do is start to, I should, by the way, pause for any questions. Anybody? Anything that I went too fast on? Okay. This used to happen to me with my students. I would say something like that and everybody's bashful. So, oh, I'm the only one who thinks of that question. So don't feel like that. The way we can analyze antennas is to take these two concepts here, these two things, the way we're looking at this, and we can put them together and we can start. Remember, each one of these things, by the way, each one of these equations has a current times a short distance, a delta L. A delta L would be like, you can choose it to be like, if you're dealing with an antenna that's like at 160, you can make it like 6 inches long or a few centimeters. So you can make that as that distance. And what you can do is, and this is how modern programs and antenna analysis work, you can break up your antenna into a series of segments, okay? And each one of your segments is got a certain length and a current assigned to it, okay? So we have this one will have some current, and I'm gonna call this one I1. This one will be I2. They're not the same. Turns out the current changes as it goes down the wire. And this is very important when you're considering different types of antenna. How that antenna current changes is real important. And oops. And then we're going to go out here. And then finally, at the end of our antenna, we have the last thing, the last current. And each one of these is delta L long, okay? And they're all this small length, but they're different currents. And we're going to see how those vary. So we've got this wire antenna, and we got these varying currents, different currents are flowing through it. And each one of those is sending out a field towards the receiver point. Some of these are not going to be straight lines, but believe me, they are. And they all arrive there, and they're all not necessarily in phase, but they all arrive at some point which is the guy you're trying to talk to, okay? And what we can do is we can add up the powers from these. Actually, we add up the fields first, and then you add up the powers from those fields, and you get a power received here from the entire antenna. So we started off by saying, okay, each one of these segments is going to generate a certain field by itself, a certain electrical field, certain magnetic field, and we can look at the power there, okay? We now can take this and we can build up an antenna model for various antennas, and this is what the modern computer antenna programs do. Like you can draw a wire or some kind of complex antenna, and it will figure this all out for you. It'll figure out what these currents are. It'll figure out what the power is, how the fields are adding at this point. And by the way, like I said, these fields don't always add perfectly together. It's not like, well, if this has got putting out a quarter watt and this is a quarter watt and this is a quarter watt and so forth, you don't necessarily end up with the sum of all that power here. These fields will interfere with each other, and this produces an antenna pattern, which is also important. Where is your antenna putting out the most power? So like, for example, it turns out that if we have a dipole, half-wave dipole, so it's got 2 quarter wavelength wires, and it's being fed by our little transmitter here in the middle, and it's going to be generating a pattern of power. Well, it turns out if you're straight off the ends, if I draw a line straight away from the center here, you get lots of power. If I'm saying the distance from this point here is proportional to how much power I'm getting. And then going the other way, we also get a lot of power. If we go off the ends, it turns out all of these values, they cancel. And they also are not very strong to begin with, because it turns out one of the things that Maxwell equation says, if you've got a wire with current going through it, most of the radiation goes away from it perpendicular to the wire. And so if we do this for all of these points, we will find that we get this sort of figure 8 pattern, which is what so we would measure this. And this is how antenna patterns are done. You can do this. I mean, you can take a meter or a radio and walk around your antenna if you really want to do that on a cold winter night. But you can figure out a pattern either mathematically or whatever. But this is the dipole pattern. It's like a figure 8. And you get most of the radiation is in 2 directions. And there's practically none off the ends. So this is why sometimes if you are targeting a particular area, you may have to move your wire antenna around or rotate it or whatever you have to do. But this has to do with how we add those up. But again, here's the kicker though. The amount of power coming out of here is the proportional to the currents flowing here and the lengths of the wire. So again, so if you have little current, they don't add up very much. Okay, they're not going to have a whole lot of power. Even if you have a long wire, you don't have a lot of power going out. If you have a short wire, for whatever reason, you have a small antenna, you're going to be, you're giving up, you may have to make that as a compromise, you're giving up your ability to radiate. In other words, you're not getting that energy out there so that your friend in another country or another part of the world can hear you. Okay, so that is the key here. So that leads also into a number of things which we're going to talk about more here. And let's, by the way, while we're at it, that's a dipole pattern. If we look at a vertical, so we've got a vertical here over a ground. So this is a quarter wavelength. It radiates like a half dipole. Now, by the way, this is assuming you have a perfect ground So this is like AM radio stations. This is what they broadcast with. This is how they get their power out. Turns out this will not be quite like this over your typical ground that you would find in the world. But if you happen to be over seawater or some like a sheet of metal, you would get out. Most of your energy is going off this way, again, perpendicular to the wire, okay? Or well, in this case, it would be a pole, a mast, or something like this. So here's a pop quiz. If I put the same current into this vertical as I did into the dipole, which will put out more power at a distant point? Remember, this is a quarter wavelength. This is also a quarter wavelength. And this is a single quarter wavelength. Same current. Which one's going to put out more power? Anybody?
Power should be equal.
Not with the same current. I'm saying current now.
Wouldn't it
The
depend
dipole?
on the ground?
Yeah.
The dipole? How many people think it's a dipole? A lot of you. Okay, how many people think it's the vertical? Anybody? Sing out. I can't see everybody's face. Okay.
Wouldn't they be equal?
No, if it's the same, see, there's the key here. The same current. Okay, remember. So it turns out that if you have the vertical, you have the shorter distance, don't you? You only have half the wire that you do here. Okay, so for the same current, you are putting out less power. Remember that. Remember that. For the same current, you're putting out less power. This is going to get into something which we'll bring up in just a second here. So hold on to that thought. Same current, less power. So I'm going to deal with something here before we get into that a little bit. But remember that, same current, less power. So let's talk about matching for a second, because this is going to ask a question. Matching is looking at, you have a generator called your transmitter, and it puts energy into a cable. This is a long piece of coax. Sorry, it's not a very well drawn piece of coax. And we want to deliver this to some kind of load. Okay. This generator here, we want to generate a lot of power, and we want most of the maximum amount of power to go in that load. Well, it turns out that if this load is 50 ohms and this cable is a 50 ohm cable, that means you'll have maximum power delivered. You won't have any reflections. This is the principle of matching. In other words, it turns out also your transmitter has a certain amount of output resistance, which is also 50 ohms. It expects to see 50 ohms. So if everybody is 50 ohms, everybody's matched. We're all going to dance together, and we're going to get the maximum power to the load. Okay. A lot of people think this is what really kills them as far as their radios getting out. Can be, but not always. So let's look at what matching means. So we would have a mismatch if we didn't use a 50 ohm cable, or this load wasn't 50 ohms. Okay. So this is, you can have some kind of mismatch. And a mismatch means that if this was generating 100 watts, you may not get 100 watts at the load. You will get something less. Okay. The question is, how much less? So typically amateurs use the concept of voltage standing wave ratio. Some people call it VSWR, some people call it SWR, things like that. And it's usually expressed as a ratio. And it is the ratio, really, what this ratio is the ratio of if you measured the voltage or current along this line, if it's perfectly matched, it will be the same all the way through. So if you put in 1 amp here, you get 1 amp out here. In the case of a mismatched cable, you will get what's called a standing wave. The current or the voltage will not be the same. It will vary as you go down the cable. And this has to do with reflections and things like that. And the VSWR is the ratio of its peak to minimum voltage. They're not the same, okay? So we get this and we say, all right, let's say, and we have meters that measure this for us. They're on your radio, or you can buy meters, you put them in the cable and they will tell you what you are getting to, how well your cable is matched to whatever you're talking to. So if we looked at this, the VSWR and looked at what is the percentage power delivered to the load, well, in the case of 1-to-1, it's 100%. In the case of 2-to-1, it's 88.9%, which is that's pretty good. 3-to-1, you're starting to really get hurt here. You're only getting 3/4 of the power. That's a 5. And finally, at 4-to-1, you're getting you're getting less than 2/3. Excuse me. So by looking at this and saying, okay, you can see here that up to about 2-to-1, we're getting most of our power to the load. The question is, where's the rest of the power going? Well, power doesn't just go into space, except if we're radiating, but we're not radiating here. The rest of the power actually comes back and heats up your transmitter. And it can actually hurt it if you're not careful. So if you'll notice here, so if I'm putting out 100 watts, in the case of 1-to-1, I'm getting 100% to the load. 2-to-1, I'm only getting 10%. It means 10 watts is coming back and trying to warm up my transmitter. And by 3-to-1, I'm getting 25 watts coming back there. That's a soldering iron. So you got to be careful with that. Definitely at 4-to-1, you got a lot of power coming back. Okay, you're getting 30 watts back to your transmitter, 33, 36 watts. So where this comes in is important is in modern solid state transmitters. In the days of the old tube transmitters, you could get really bad matches, and you were not putting out as much power as you thought, and you were just warming up those tubes just a little more, and tubes could take it to a point. But with the advent of solid state became more sensitive to that. I would recommend that you don't exceed 2-to-1, because what can happen there is you can get excess voltages and currents back at your transmitter, which could damage the solid state components. And you have to be careful about that. There are ways of getting around this. One is a tuner. A tuner will adjust the match for you. It gets in the middle. It acts like a go-between, and it says, okay, look, I know you guys don't like each other, but I'll try to shove as much power across here without anybody getting hurt, okay? That what you're giving up, though, is even though you have a tuner in this line, you're still not going to get full power to the load. All it does is it makes the transmitter play nice with everybody else. Typically, the tuner is located in the transmitter these days. Actually, the best place for it is as close to the antenna as possible, but that's not always practical. You can't have a tuner floating up on your dipole that's, several, 40 or 50 feet or, tens of meters above the ground. So the key here is just remember that you're always trying to get, I would suggest that you stay below 2 to 1. And this will protect your transmitter. If you must use a tuner, go ahead. But remember, if you are using a tuner with a mismatch, you are giving up power. You're giving up power to the power to the load will not be any more than this. Okay. In fact, it'll be a little bit less. Tuners also.
Does that power go anywhere that's not now going back into the radio?
So it actually ends up, what you're doing is you will get more, you will get the power delivered there, but you will also, your tuner will warm up, literally. So there are, you are avoiding it depends on where you are. So if the tuner is here, typically where that power goes ends up heating up your cable, literally. You can get cable losses here, or you can get other effects, like there's going to be heating, but that power eventually will go someplace, and it's not usually to radiation. Okay, does that answer your question?
Yes, thank you.
With the balloon?
Okay. Any other questions?
What happens if you put a balloon in it?
A balloon or a balun? Okay,
Yeah,
so
balun,
a balun is a matching circuit. Again, if you put it here, you're not matching the cable. So let's say this was 200 ohms, okay? If I used a 4-to-1 balun, I would have basically, I would be matching the cable. So a 4-to-1 balun, a balun, by the way, is a form of transformer. A 1-to-1 balun basically has the characteristic where the input impedance or resistance is the same as the load. The gentleman has suggested, why don't we put a balun in here? And that would be an easy thing to do. But remember, it only works well if your antenna, first of all, is a resistance. And secondly, if the feed point impedance, which we're going to go back and talk about now, happens to be the right ratio. In other words, basically you have a transformer, and this is not necessarily how it's formed, by the way, but essentially this is what it looks like. There is a ratio of impedances of 4-to-1. And so on this side, we could have 200 ohms. And on this side, it would look like 50. Okay. You'd have some heating in the transformer, some loss, but it would be certainly not what you would have if you tried to match 200 to 50 ohms directly. So a balun here would help, not here. A balun at your antenna would help. Okay? Any other questions?
If you're using a tuner and you've got a 2-to-1 configuration between transmitter and antenna, you put a tuner in there, are you still just losing, even though it's lying to the transceiver and saying, this is 50 ohms, don't worry about it?
Yeah.
Are you still losing 88.9%? Is the loss the same, or is the loss greater?
The loss actually it'll be, in this case, it'll be roughly, you're going to lose some heat in the tuner itself because of coils. Coils they have their own internal losses, as we're going to see, because sometimes they're used in antennas. There are going to be some losses there. There will also be losses. If you have it here, you're going to heat up the cable because you're going to have some currents in here, which will be still high. Remember, this is current too. This is voltage and current. So you may have a current here that is very high, and nothing is a perfect conductor, even copper. So you have some resistance there. Things heat up. You will get losses there. It's hard to say. It depends on how bad the match is up here. But you will make things better. One thing that, by the way, you will definitely avoid is modern solid-state transmitters have safety circuits in them. They will try and say, look, I'm going to save myself. You're a moron, but I am not going to die because you can't match your antenna. And so I'm going to turn down my power so that I don't see this, 800 watts coming flying back at me. And so therefore you end up lowering your power that way. Essentially, with 2 to 1, you could probably get away with a tuner, and you might get a little more power down here, depending, again, it depends a lot on the cable, its length, and everything like that.
I have a question.
Yeah, go ahead.
What might cause a difference in SWR between measuring the antenna right at the transmitter itself, but disconnected from the transmitter? In other words, all of the coax and the whole system. You get one measurement there on a Rig Expert SWR meter, and then I get another measurement when I connect the cable to the transmitter.
Right.
On the transmitter itself, again with the antenna tuner not in line.
So where is the SWR?
It's considerably better on the what number is it?
No, wait, I'm sorry, I'm trying to figure out your configuration. So you have an SWR, this thing which measures SWR. It has a generator in it. Is that right?
It's just a meter. It's just a little Rig Expert meter.
So
generate you.
Sorry?
Generate a signal. Rig Expert.
It's
like a mini transmitter.
It's a generator. It generates a signal and measures back. So
that's what I thought. Yeah. So it's generating a signal, and so when you have basically it's in the circuit like this. This is the Rig Expert. You're looking at the cable and everything like that. How are you connecting this when you have the transmitter? Where's the transmitter being connected?
I just connect the antenna cable, disconnected from the Rig Expert, connected to the transmitter itself.
I
radio
see.
rig. So the
And
cable
your
remains.
rig is measuring a different SWR than
That's
what
right.
the Rig Expert. Gotcha.
That's correct.
So, what's the difference? What is one seeing versus the other?
The meter itself shows very good SWR, less than 2 to 1, probably around 1 point, maybe to 2, 1.2.
Good.
And the SWR from the transmitter is considerably higher, up over 4.
Ooh.
I would say. And nothing has changed except I've switched out the meter for the transmitter.
So basically, you've unplugged this part here. You've unplugged it, which was the SWR meter, and you've plugged in a transmitter.
That's correct.
And
That's
the
exactly
transmitter
right.
is telling you have bad SWR.
Yes, that's correct. Which is correctable or matched, I should say, by either the antenna tuner inside the transmitter if I choose to put it in line, or an outboarded tuner. In other words, I can use the antenna. But why am I getting 2 different readings when the only thing that's different is how
strange.
I'm measuring it?
That's a good one.
Okay.
We can actually discuss that more. I'd like to get finished here, but that's something we can pick up if anybody's had that experience. I've had it. Sometimes you hook it up and one says 1.1 and the transmitter says 1.2. The only thing I can think of that's really an obvious problem there would be that there's something wrong with the SWR meter in the transmitter, or you've got the tuner left in.
Jay,
Yeah.
this is Mark. I've had that experience, and what caused it at my situation was less than perfect match at the antenna end of the coax, and the SWR varies along the length of the coax. And with the Rig Expert, you have a given fixed length to the meter, whereas if you go directly into the transceiver, the length of connecting wire between its internal SWR bridge and the cable is different. And in fact, sometimes adding a little bit of coax in series with the existing coax line will give you a much different SWR reading on the internal SWR bridge.
Yeah,
Okay.
I would tend to discount that because his match is so good. I mean, the rig expert is telling him he's practically 1.2 to 1,
That's
which
right.
is, you know, used
But
to
I've had things like that, Jay, where
Okay.
the SWR would be like 1.8, 1.9 to 1, and add a couple of feet of coax on a given band, and the
Oh.
SWR indicated would go way, way down.
So
Yeah,
which one do you believe?
yeah, which one do you believe?
The one that
I
keeps the
would tend to believe it depends on how, first of all, how the SWR is being measured. There are several ways to measure SWR, and I'm not sure how the rig expert is doing it, but I have a feeling it's probably much the same. It's a line sampling, and it should be the same. I wouldn't expect a wild difference, especially with gentleman's a good match like what he had. But I want to go on and finish this up here, and we can talk about that some more.
Thank you.
Okay. But anyway, we've been talking about matching here. Okay, and as we can see that, you know, we have to be careful. We'd like to keep things down a little bit, even, and if you want to use a tuner, fine, but you still, with a length of cable like this and a mismatch, even with your tuner here, you're going to lose the power being delivered to the load will not be what you want, okay, not full power. So we'd like to understand, okay, I put a 50 ohm load here. Okay, great. That's a resistor. We all can go out and buy a dummy load. Okay, basically a dummy load is a big resistor in I have one here. So dummy load, okay. Inside, if you look carefully inside here, I guess you can't see it. There is a big long resistor, piece of carbon here, running from end to end connected to the coax connector. So that looks like a resistor. Okay, that's what happens. You put current into a resistor, what happens? It warms up. It radiates the energy as heat. It goes off as heat and never comes back. So let's look at what our antenna is. Our antenna, basically, if we're good boys and girls, will basically take energy and it radiates it as heat. So we've got our little antenna here. This is our little dipole and our transmitter in the middle here. And we have around it this sphere, okay, that we talked about before. We put some current in here. We get some current flowing in the antenna at the feed point. We can measure the total power that's crossing this sphere, okay? That's how much energy power is radiating out of here. That's how much energy per second is flowing out into space. It never comes back. So what does this remind us of? It's a resistor. I'm putting current into two terminals. If I had these two terminals in a box and I put a 7 megahertz signal in there, a certain amount of current, and I ran outside and I had this magical device that would measure all the power crossing this giant sphere that's 10 miles across. Okay. There would be a relationship here. I have a certain amount of current going in here, and I have a certain amount of power leaving. Okay. I don't have any other power sneaking in here. Okay, and I have drawn this sphere so that no power can get past me. It will not leak around me. I am looking at everything coming out of here. Now, from the standpoint, if I looked at this and I had two terminals, or the coax thing, oops, wrong end, coax, that's got two terminals on it. How do I know, how do I tell the difference between putting energy or current into those two terminals and putting current into this antenna? Both are taking power. Power is flowing out of them, never to return. Okay. So most of you, if you're taking your amateur exams, should know what's the relationship between current and power. Well, basically it would be okay. The total power here has to be, if there's no other sources of power floating around in here, is the current squared times some resistance. That's what this is acting like. It's a resistance because I'm putting, it can be modeled that way. I am putting current into it and it requires power. That power flows out, never to return. And this can be modeled as a resistor. So this antenna is acting like a resistor. Okay? So we call this the radiation resistance. Okay? The radiation resistance. This is what the antenna looks like. So if I have a certain amount of current flowing into this antenna and this amount of power is going outbound, I can say my antenna looks like 50 ohms, depending on how much power is being radiated versus how much current is going in. Okay? But let's remember something. I said current. Remember before I said with the vertical, we are getting less power for the same current than the dipole, okay? The dipole, if I put the same current in both of these, the dipole puts out more power. How do I account for this here? The radiation resistance is different for each one of those. It turns out a dipole has by the way, a perfect half-wave dipole has a radiation resistance of 73 ohms. In other words, for the same amount of current, notice what happens here. If I have I squared times 73 ohms, I will get a certain amount of power. If I have 1 amp going in here, I have 1 amp squared, 1 times 73, 73 watts. If I have a vertical, now what do I have? Well, it turns out a vertical is 50 ohms, thereabouts. Okay? So a vertical looks like 50 ohms. Notice for the same current, what do I get? I get 50 watts. It's less current. I'm sorry, less power for the same current. But watch what happens though. If I put 50 watts into here, I would have less current, but I'd have the same power. And it turns out power in is power out. If most of your energy is going into radiation resistance. So the same power going into a vertical, a quarter wave vertical, will give the same power as if output as if you put it in a dipole. Okay? There's differences in the radiation pattern and things like that, but the current is different. Okay? If I put 50 watts into 73 ohms, it's a smaller current, okay, and it balances that out.
Need cash?
Sorry?
For your nails?
I'm sorry, somebody has got a mic open. Anyway, so we're not violating any laws of physics here. But remember before I was talking about the current versus between the two. And that's why the radiation resistance is different. When you match a line to a dipole versus a vertical, okay, you get slightly different, like for example, a dipole will get close to a 1-to-1 SWR, depending on how you cut it and everything like that. There's ways of making it close to 50 ohms, but if you drive it directly with a 50 ohm coax, you're not going to get a real match, a perfect match. Whereas a vertical, you'll get close to one, okay? But notice something here. We can assign a value to this. We can say, okay, we know that a dipole needs, it looks like 73 ohms. A vertical looks like 50 ohms. And then we can use this to start talking about efficiency. Efficiency is one of the biggest problems with limited space antennas. This is where you can really get yourself hurt. You think you've got, oh, look, I've got a perfect match here. Yes, I can make a resistor look like 50 ohms. I buy a 50 ohm resistor. Does it radiate? No. Okay. The question is, now we can look at what happens when we take power and put it into an antenna that is not a vertical or a dipole or is some other kind of antenna. What happens? So oftentimes when people want to work on the low bands and have limited space, you end up with papers that are stuck together. You end up with problems where you have things that are robbing you of power. So let's say we had a full vertical here, and it looks like, and it's over a ground. And this ground, by the way, is a perfect ground. It's a beautiful ground. Okay. So there's no resistance in this ground. It's like a sheet of aluminum that goes on forever. Go find one of those. Anyway, here we have our quarter wave antenna. This would look like 50 ohms in here, and basically 50, you would put a coax to that and you would get most of your, if not all of your power going out. But everything has resistance, everything in the real world. And it turns out that you would lose, even in this case, you would lose a tiny amount of power because of resistance of conductors. Sometimes what happens, you think of like, let's say you have a number 12 wire. I'm talking about an American wire gauge wire. So it's about 3 millimeters across, copper. And we use that in house wiring, okay? So fine, you put it in your house wiring. What's the resistance? You get out your ohm meter and you measure the resistance of the wire and you say, oh, look, I've got 1,000 feet of this and it's a half an ohm, or let's say, okay? It's not a half an ohm at 7 megahertz. It's like a lot larger, okay? The reason is, as you go up in frequency, less of the energy flows in the wire, or the current flows in a smaller and smaller area. You can't have the wire, the inside of the wire is shielded by the outside of the wire. You know how copper shields, they shield energy from crossing over and, you know, keep one part of the circuit from talking to another part. Well, the wire is shielding it from itself. The inner side of the wire, right at the center, doesn't even know that, you know, that anything's going on the outside, because it's got a lot of copper between it and the surface. Most of the energy, most of the current flows along the surface, which is why, first of all, you can use tubing as a good antenna, but you will get some losses here. The question is it really significant? Well, it turns out if you had your 12 gauge wire, you get about 1.1 ohms for a 40 meter wire. If you made this a wired vertical. And so we can say that, let's look at how this would be affected. Well, we would look at what would be the power being dissipated by the 50 ohm resistor, and then what would be the total power that's being dissipated by the system. So you have, basically the system looks like you have this 1.1 ohm resistor in series with your radiation resistance, okay? And if you put a current through here, you're going to get I squared times 1.1, and then you're going to get I squared times 50. Those will be the two different powers. And if you looked at the total, basically, cut to the chase here, your efficiency is your radiation resistance divided by the sum of all your losses. And you can see here, this is very close to 1. In fact, I calculate, I think it's, what did I say? It was like 98%, something like that. You can look at that and calculate that. Yeah, 98.6% or so. So it's almost negligible. You're heating up the wire, but most of the energy is going off into space. Now let's look at another one. You've decided, well, gee whiz, I can't put up a 10-meter vertical in my backyard or on the top of my house or anything like that. There'll be some complaints about that. And I have to put this over a real ground. I live in Lower Slobovia or whatever, and we have the ground I got, okay? Turns out ground is not a very good conductor. And so you will end up with putting this up, and oh, by the way, you want this to be shorter, so you get out the ARRL handbook and you put in a coil to make the antenna shorter. This is not to scale. This is a lot less than a quarter wavelength now, the total height. Okay, for the same, this will resonate, it'll work at 40 meters, and it looks like 50 ohms. Okay, so you're saying, well, what's the difference? A couple of things. One, the radiation resistance is smaller. Why? Because I've got the same current, but it's flowing over a shorter distance. Remember, power, the power transmitted is based on, it's proportional to the current times the length. If I've got less length, that means the same current is putting out less power. What happens to the radiation resistance? Well, if you look at that, if I have, this is smaller for the same current, R must go down. Radiation resistance, as you shrink your antenna, goes down, okay? So now, even though this looks like 50 ohms, where is the rest of it? Well, it turns out you've got a certain amount in this coil. Coils have losses, and that has to do with the construction, the wire, everything that's going on with them. And you may end up like, for example, in this case, you have got a very short, let's say you had an 8-foot, this is only 8 foot or about 2.5 meters. You have a coil here, you need 33 microhenries. It turns out this has a resistance of, I'm looking for it, I figured this all out beforehand. So you have, what's that? Here it is. This is, by the way, the radiation resistance of this is 3 ohms. If this is only 2.5 meters. Instead of the 10 meters, the radiation resistance goes down, and you can have a resistance from this coil of 36 ohms. Excuse me. So this can have a loss. Notice here, your efficiency is going to be terrible. You're losing a lot more power because if you look at this, you have 3/39%, or 3/39 is your efficiency, which turns out to be about 7.7%. If I'm going off the screen, I apologize. I guess I'm still there. So what happens is you are giving up for making this a smaller antenna. You're sacrificing some things, and you should be aware of them. If you're going to do it, you'll still get out, you'll still hear things, but a lot of your power is going away. And also, this assumes still we had a good ground here. A real ground, you just put a stake in the ground at the base of your antenna, you're going to be heating up all the little worms under your antenna. You're going to have worms crawling out of the ground because it's getting too warm under there, because you're warming up the ground. That's where also, that would be a huge, that would make this even worse. which is why if you have small antennas, you must have good connections, and why, for example, in the case of a vertical like this, you would want to have radials. Radials are pieces of wire. If you're looking from the tower down, I'm looking down from the top of the vertical. They are arranged in a star pattern, and you typically want them to be a half wavelength or better, at least a quarter, but a half is good. And you want as many as possible. And you want them, don't bury them, you lay them on the ground, but unfortunately, some of us have to bury them because they get tangled up in the lawnmower if you're trying to mow around your tower. And so you want to have these as close to the surface as possible, especially if you have a small antenna, or even if you have a big one. If you got a full size, again, you want radials, because in a vertical, this will cause losses which affect your efficiency. So I'm watching my time here. I want to talk a little bit about some various antennas that we're using, and in the interest of time, I'm going to just talk about, I've already talked about the short antenna. The short antenna, you're sacrificing to get the size, you're sacrificing your efficiency, and you must have a good ground with it. Let's say if you're using a vertical, or even if you're using a dipole, these coils will be in series. Again, you're just basically having two verticals side by side, and so therefore the efficiency will still be low. One thing about a lot of people want to use something called a random wire and a tuner. So basically you have somewhere you have a tuner set up. This is often used on boats, and they're automatic tuners, and you have this basically a wire that's going off, and it's some length, and you want to use this on multiple bands. Well, one is a good ground is important, but you should understand what this thing looks like at various frequencies. And it turns out you can look at it, and it has a very interesting diagram for its resistance. And I'm just going to do a few turns around here. This is inductive, this is capacitive. In other words, the antenna is non-resonant. And this impedance is at, when the antenna is 1/4 wavelength long, when it's 1/2 wavelength long, when this one is now 1.5, sorry, 1 3/4, sorry, and so forth. This would be 1 wavelength. And as you can see, when you have a low impedance here, and when you go out to a 1/2 wavelength and you're feeding it, and by the way, that would be from this point to this point, you would get varying impedances, and they vary quite a bit. So for example, in the case of a 1/2 wavelength, this is almost infinity. It's very large. This would be 50 ohms here. This would not be 75 ohms, because you're feeding it from the end, and you will get something very, very large. As you go up in frequency, where the antenna is becoming multiple wavelengths, these begin to get closer and closer together. Notice that if you're not on a perfect frequency, you're not right on the antenna is not a perfect harmonic length, you will get significant series inductance and capacitance, which affects your match, and that has to be made up for by your tuner. And what can happen, especially if you hit this one, let's say this is 160, you're putting a lot of strain on your tuner. You can get very large voltages inside, especially if you're running high power, and you can get flashover. Okay, so be aware of that when you're choosing. They often call this a random wire. Well, it shouldn't really be random. You should try to choose it so that it has a good harmonic relationship, so that you're on most of the bands, you're hitting one of these points. It makes it a little easier on your tuner. And with that, since we've gone pretty late here, I'm going to wrap this up and open it up to questions. So basically what we've seen is we can review this a little bit. First of all, what's important is that's what gets you out there. Current and length. If you are compromising, usually this is where you compromise, you are going to have, if you have less than a quarter wavelength, or you're less than a half for a vertical, or a half wavelength for a dipole, you're going to have small radiation resistance, and that's going to lead to inefficiency. Be aware of that. Tuners and match, okay, is important basically to save the transmitter. But you will get losses if you're not perfect. So if you are greater than 3-to-1, or actually 2-to-1, if you're much above that, you really should be using a tuner, but you also are going to be sacrificing efficiency. Also, we saw that that we can look at how this relates, as I said, with various types of antennas, with random wires. You want to make sure that you look for harmonic lengths. Remember, most of the ham bands, except the warp bands, are harmonically related, 160 all the way up to 10 meters. So, and in general, you can look at this and say, all right, what is it that my antenna is doing? What can I expect from it? And you can get an idea of what you're giving up for what you're getting. And I think that's probably all the farther I would go. Boy, good look. You know, old habits die hard. This is the links of one of my lectures. And I'm sorry that I put you through that. But anyway, I'll open it up for questions if anybody is still awake.
I have a question about radials.
About radials.
Yeah, how many radials do you want to put on the vertical? How you have to spread them out?
Okay, you can get away with, if I came out of broadcasting, and we used to, if you had 120 radials, okay, you're basically putting them every 3 degrees. And that's overkill for most amateur situations. Typically, you can get away with 4, depending on how efficient your antenna is. In other words, if it's a real short antenna, yeah, you want the 120. Because you're starting, it basically, you can think of it as resistors in parallel. So if you got one radial, and let's say it's 2 ohms, it looks like, let's say we magically work that out, it's 2 ohms. Well, you put in another one, now you're down to 1 ohm. You put in 4, you're down to a half an ohm. You see what happens there. It goes down as the number. So it's basically the resistance drops as the number of radials. At a certain point, it becomes, is the copper worth it? You know, it depends again on what your radiation resistance, how short is that vertical? Like I said, if you got an 8-foot vertical, normally you use like that on a car or a truck. You know, you've got a sheet metal ground, which works very well. But if you're really laying that out in your backyard, or you have a very short antenna, yeah, you're going to want a lot of verticals. I have a tower out back, which I use for 160. I have 16 radials on it, and I find that works very well. It's a fairly good sized tower, so it's not a full quarter wave, but it's close. Any other questions?
Yes. May I?
Yeah, go ahead.
Yeah. Well, thanks very much for the very, very nice and comprehensive talk. The beginning, when you showed the integral of the magnetic electric field cross the complex conjugate of the magnetic field. I think I remember that that yielded a quantity that was proportional to the delta L squared.
Yeah, I'm trying, where did I put that? Where's my, darn. It's the problem with, hold on a second, I passed that around. Yeah, I remember that, hold on. Trying to keep these things in order. Ah, here we are. Got stuck together. Yes.
Yeah.
Hang on, there it is.
Yeah.
Yes.
Yeah, that's right. So the power was proportional to delta L squared.
That's the radiated power traveling. If you integrate and you look at the entire surface around the antenna, that's how much would be radiated.
Right. So when we are talking about the length of the radiated power of the dipole as compared to the radiated power of the vertical antenna, from that expression for a given intensity, the radiated power of the vertical antenna would be 1/4 of that of the dipole, because it has half of the length.
Yeah.
However, this is not consistent with the result that is obtained with the 73 ohm and 50 ohm from
Right.
the right. Why?
It has to do with the current distributions. Okay. The current distributions are slightly different for each one of those.
Mhm.
You have, oh dear. Yeah, that's the best way I can explain it without going it heavy duty into the math. So it has to do with the current distributions along those. And so if you have, this says, by the way, this is the integral of the, I'm sorry, the incremental length. Okay, this is not the entire length because I is not.
No, this is these differential lengths of.
Yes, this is differential lengths. Yes, so this would be for each differential. Does everybody understand this? This is kind of we're getting a little bit into the math. This is assuming you've got your little 6-inch section or your 3 centimeter section of your incremental length, and it's got a certain current in it. Okay. Notice this is under the square here as well. And as you add those up, they will, each one of them contribute to your radiated power. Okay. And so that's where the part of the discrepancy comes from. And that's, like I said, it's the current distribution.
Okay. Thanks.
Certainly.
I have a question.
Oh. We got a tie here. Let's see. Yes, Mr. Dennis, I guess it is. Is that right?
Yes, sir.
Yeah.
I have a question specifically towards magnetic loops. Okay, so by this equation, a small transmitting magnetic loop has poor efficiency to begin with.
Yeah, it depends, like, of course, on the size of the loop. I mean, if you have, what size are we talking about? What's the total length around the loop?
I would say about 10 feet for 40 meters.
Oh my.
Yeah, I'm pushing it already. So let's
Yeah.
just say using the same one just for 20 meters, I get a little bit better performance.
Yes.
However, my question is, how do I improve its efficiency knowing that it's poorly efficient to begin with?
Well, how are you matching it?
I'm using an air variable capacitor.
Okay, so you
match
basically.
Okay.
Okay.
Secondly, is I minimized the length of the transmission line, or the coax to the antenna.
Well, transmission line is proper, yeah.
And then all joints, any connections whatsoever are soldered as much as possible.
And what's the loop made out of?
copper tubing, and I used
Oh.
the skin effect to try
Yeah.
to improve that.
Then you've done you've done what you could.
Okay.
Yeah,
Alright.
I can't think of anything else that you could possibly do there. The air variable capacitor. Yeah, I'm trying to see how you're doing, but what when you adjust the capacitor, you might be getting a mismatch there. You may need some other kind of network. Just a series that's of air variable in series or in parallel.
In parallel.
Oh, yeah, you should look at the network there. You may need a different matching network.
Okay.
Play the diameter of the copper tubing a role?
Sorry again?
Plays the diameter of the copper tubing a role?
I'm sorry, I'm not hearing him very well.
By a loop, the diameter of the copper tubing.
Oh.
Is this playing a role?
Is it playing a role? Yeah.
Yes, because it affects the radiation resistance. So the larger the loop, you're approaching the cubical quad. Okay, if you bring that out as a large loop, if it becomes a significant antenna there, and it radiates actually fairly well. Okay, but if you've got you said 8 foot. No, I'm sorry. What did you say was the?
It was 10 feet.
10
roughly,
feet.
Yeah.
So that's 10 feet. The length of tubing, or 10 feet is the diameter?
10 feet is the length of tubing that comes out to about a yard or a little over 3 feet.
Yeah.
And the only reason why that's the case is because the tubing was sold at a 10-foot
Yeah. And that's exactly what we work with. What we get, we're not. Yeah, a broadcast engineer would look at that and say, no, we're going to spend X $1,000s to get the right length here and everything. And by the way, do you know the story about the cubical quad? No, that's a great story about how that was invented. But that was basically done. There was a religious station after the Second World War called HCJB, which is in Ecuador. And it was outside of Quito, and the transmitter site was located up at around 10,000 feet, so that you have rarefied air. And they were putting out, 50, 100 kilowatts to signals, and they were using a dipole. And it was flashing over at the end. It had corona off the end of the dipole. And there was people, the local population was hearing what they considered the voice of God, because there was all this religious broadcasting, and the arcs off the end would actually create sound, which would sound like a person's voice. Anyway, so what they did was they invented this idea of a magnetic loop, because it has no voltage nodes. It doesn't have the high voltage on the tips. And they were literally, their dipole was getting shorter because it was burning off the tips of these things. So they made a magnetic loop. So the magnetic loop is a good antenna. It just got to be a little bit bigger if you can do it. So, and you might look at your matching network. You might need more than just a series capacitor. Anybody else?
I have a question.
Yeah, go ahead. That's Al, is that?
Yes, thanks. Generally speaking, in a field day environment, we're talking a lot about coax. Wait a minute. Sorry, I didn't know if you could hear me. We're speaking a lot about coax, but I like to use ladder line. And my curiosity was, can I put up a length of a doublet fed by and what's the issue with picking up maybe interference from the feed line as compared to the coax? Thanks.
Well, yeah, you have something. What you're talking about is an off-centered dipole. And it turns out that you can feed a dipole at a point if it's resonant. In other words, it's a full length. If you feed it off center, this 73 ohms is not 73 ohms. It turns out that if you feed it at a point here, this current goes down as we approach the ends of the dipole. It's got to be 0 at the ends, or very near 0, because at the end of the dipole, there's no place for the current to go. And so Professor Kirchhoff came along and said, well, wait a minute, you can't pile up charge here because you'll end up with all the charge in the universe at this one end, and you'll get lightning bolts, or the power will go out in the universe and they'll blame you. So you have to have this current distribution where it's forced by there's various reasons for it. One of them, you can look at this as an open transmission line. You're sending out current this way, it hits the end, and it has to turn around and come right back, okay? And it's out of phase. And so at the end, it exactly cancels to zero, and as you come back, it starts to add, so you get the maximum current in the middle. This current will have a sine distribution, basically, very close to it. And if you work this out, you can say, well, if I feed current here, if I feed this lower current here at this point, I will get this current distribution, it turns out, and I will get the same radiation. And so you can figure out that your radiation or feed impedance is basically this rough equation here, which is the 73 ohms divided by the sine of pi times this distance from the end divided by the total length, okay? And if you put this at like the half current point, you end up with about 292 ohms, which is very close to 300, and you could feed it here. The question is about ladder line pickup. Ladder line, unlike coax, if you have coax that's laid, you can run two pieces of coax almost next to each other and get very little crosstalk. Ladder line, you can't do that. Okay, the fields cancel when they are a significant distance apart, and that's what keeps them from talking to each other. So you want to keep ladder line away from other things. Like, for example, you cannot run ladder line across a conductor like this. If you had a piece and laying on a piece of metal, you'll screw it up. Okay, it has to be basically in the air and a significant distance dependent on frequency. You have to keep it away from other objects, otherwise you will get crosstalk. But you can do something like this if it helps you. Also, one other thing you have to watch out there is this is somewhat unbalanced. And so you may get slight differences in currents, which causes a common current on your ladder line. Typically, you'll want to feed that with a balun to make sure that you don't get currents coming back and burning the noses off your operators or their fingers on the key. Okay.
Thank you.
Sir, any other questions?
Yeah, I have just one more question.
Oh.
Kind of a philosophical one. Thanks for reminding us about all of the laws of physics here. But they kind of keep us prisoner in a way, don't they? And I was just wondering, from where you sit in your experience and things that you know about, is there anything we might look forward to in the next 10, 15, 20 years that would come along as a new way to use antennas, perhaps much shorter, maybe something electronic that's inserted along the way? So what's the future look like?
Well, they've done, and most of the work there has been done at higher frequencies, and they've got antennas that that are practical for various forms. For example, that you're familiar with GPS, they have what's called a patch antenna, which is very good. I would not want to do a 160 patch antenna. It would be the size of a football field. I mean, it'd be not quite a football field, but pretty big. Other things they've looked at are antennas that they put into, they'll take an antenna, let's say a dipole or let's say a vertical, and they will, so you got your vertical, and they will put it inside a block of material. So this is inside this block of material, which is not, it's not an insulator, it's a dielectric. And it has other properties, and it actually allows this to be smaller. However, we're still running into, and what happens is this acts as a boundary so that the antenna thinks it's in one world and it allows it to radiate out to the other outside world. However, you're still running into certain laws of physics. It will work as a shorter antenna. Problem is you're still running into that I times length, and you end up with and it not the radiation resistance is not there. It works, and you use that like your cell phones use it. It's called a chip antenna. But this is mostly used at high frequencies, so that, you know, this would be typically, I've drawn this really large. Typical chip antenna looks like maybe it's about a centimeter long and a few millimeters wide or square. It's like a little box, and it has a contact on one end, and it's designed to radiate at 900 megahertz or something like that. That's some of the new technology there. There is this whole thing, and I'll just bring this up. There is another solution to Maxwell's equations, and people talk about it because remember what I said about the E and the H fields falling off as by the inverse of the distance from the transmitter. And this, the power at this point actually would, if we kept doing this, it would fall off as the square of that. And so your power goes down by the square of your distance. So if you're twice as far away, you've got 4 times less power, or a quarter power. There is another solution of Maxwell's equations which says your power will drop as the inverse. That is fine. If you want to do that, you need an antenna that is the size of the universe. In other words, it has to be almost infinitely long. There are some men and people who have experimented over the years with this type of antenna, which is, it's made up of a coil and a capacitor, a giant coil and a giant capacitor. And it's designed to generate the E and the M, the H fields, you know, the electromagnetic fields separately, and then they combine together as they fly off into space. There's been some discussion as to whether or not that really works. So that's the only one that I know of, other than you know, just different materials to make things efficient and things like that. But basically, yeah, you're right up against, I'm sorry, you're dealing with free space, and free space is, unless somebody repeals the laws of physics, is going to be pretty much free space.
I have a question. Do you have time for one more?
I've got, actually, let's see. Normally I charge $152 an hour, but for you guys, a discount. Anyway, go ahead.
Oh, goody. So maybe you could tell me about the characteristics of, say, a 40-meter horizontal loop antenna.
How high are you off the ground?
It's not a half wavelength. It's more like 30, 40 feet, 30 feet probably.
Yeah. And you're using it to, what's the size of the loop?
It's 40 meters. It's total. It's a delta loop, 3 sides.
Yeah, but
total.
It's horizontal.
It's horizontal, yes.
Yeah. So, yeah, you're fighting the ground there, because you see you've got that pesky ground there, which does not, it's like, think of it as a giant resistor. And all those fields that go into it, they don't come out again. The ground just soaks it up like water. And you will get some reflection off of that, which will distort your pattern. Yeah, you're fighting altitude there. It'll work. 30 or 40 feet is not bad, but it's not the best. It'll affect your takeoff angles and things like that. Just curious, why did you go with a delta loop horizontal to try and what?
As versus 4 sides?
Yeah, I mean, or even like a rhombic.
It's availability of trees.
Yeah.
So has nothing to do with anything.
The gardener laid out your antenna farm.
That's right.
Yeah. No, but again, this is exactly what, yeah, you're fighting your altitude mostly. You might think of using one of those trees to run a 40-meter vertical, unless you're trying to take off in a certain direction or force your thing there. Yeah, you might look at that. Although, again, with a vertical, you'll want good radials. You are fighting that ground. So you're in Iowa?
Yes.
Your farmland, you got to understand something. Your signal there, where did I did some looking at that too. Your signal there will penetrate upwards of, like 20 meters, 30 feet, 60 feet down. That signal will go down there and it'll interact with whatever under there, which is dirt and water and salt. It's partially conductive, but not very good. And that will just absorb energy.
I've noticed that the worms come out when no, that's a joke. That's a joke.
Yeah, I know. Usually you want the worms to come out. You take 110 and you plug two, you put 2 posts in the ground and you will get the worms coming out. But anyway.
All right, thanks.
Sure. Anybody else?
I have a question.
Go ahead.
Yes, Heather.
All right. First of all, I've seen the worm trick before on YouTube. So where I live, there's a radio station, 98.5, and it's very close by. The transmitter's very close by, and I can hear it on 20 meters, and I don't know how to block it. It annoys me.
Okay, it depends on where it's being generated. I highly doubt it's a subharmonic. Have you tried, when you disconnect, let's see, how would I do this? What sort of antenna do you have?
I've tried a couple of antennas in a couple of locations. And I've tried a dipole and I've tried a vertical. And I've tried the vertical like directly connected to my KX2. There's no coax in between.
What kind of radio do you have, ma'am?
A KX2.
Okay.
Elecraft.
Yeah.
And yeah, I've heard it.
And
there.
Where
and
do
I've
you,
also, if
yes?
I tuned it to a different frequency, like I've heard it on like other bands as well. And I know it's 98.5 because that ID'd itself.
Oh, of course, that's excellent. Now, what you could be having is a couple of things. One is you're getting interaction, the signal's coming in and it's overloading the front end of your radio. It's coming in and it's just absolutely hammering the poor little transistors at the front of the radio, and you might be generating all kinds of different products. You also might be getting in a situation where different things that are going on inside the radio are causing mixing. Mixing is where 2 signals beat together. So the one thing to do would be to try and generate or get a filter, basically a low pass filter, to keep the signal from getting in your radio. There are filters that are made, they're not so popular anymore. They used to make them for what was called TVI. In other words, transmitters used to transmit on, let's say, 28 megahertz. 28 megahertz doubled, the second harmonic is up at 56. 56 was in the television band. And so harmonics were getting out, and they were, harmonics from the transmitter were getting out to the outside world. That said, you might try putting some kind of filter. There's various ways of doing it. You can get like a low pass filter that cuts off at like 30 megahertz.
Do you speak about the band? Do you speak about the band pass filters you can buy?
There's also band pass filters. Thank you. You also have a possibility where you can create. It requires a length of coax. You can create a notch filter, which will basically attenuate that signal. I would suggest either, as the gentleman suggested, bandpass filters. Now, bandpass filters only operate on a particular band. Do you operate on how many bands? Do you like 20 meters mostly, or do you operate on several bands?
I've tried that one. I haven't really tried other bands yet.
Okay.
Just what
So-
was convenient to try.
That's the one thing. The other thing is, and I've had it happen. How far away is the transmitter?
Half a mile?
Hmm.
Yeah, probably about the same height as the transmitter on both of my locations.
Mm-hmm. Mm-hmm. And 98.6, so it's probably a mainstream transmitter. They could be running several hundred, well, they could be, depending on where they, what's a call sign?
I don't know.
If you find out, you can send Buzz an email with that, and I can look them up, or you can actually look it up yourself. Go to something called, you can go and Google the call sign and pull up the Wikipedia listing, and at the bottom it will have the FCC database information on the transmitter, or you can go directly to the FCC database.
Okay.
And it will tell you what the power output is. Now, it's entirely possible that the transmitter's dirty. It's happened. How do you hear that? What does it sound like? Do you actually hear a voice, or what do you hear?
So if I set my radio to AM, first of
You
all, I
hear
always
it.
hear like I hear noise. If I set it to AM, I actually hear it say Island 98.5 when it IDs itself. I can identify it.
Okay. And is that at one frequency or multiple?
Multiple.
Yeah.
And they're all like multiples or like, so 98.5, if I divide it by 7, is right around where I get annoyed on 20 meters. And so I was dividing by other numbers and painfully tuning the KX2 to try to see if I could hear them, and I can.
You can?
Yes.
So you're hearing subharmonics. That's nifty. Wow. That's an interesting point. So you saying, all right, 98.6.
It's 98.5.
98.5. What would that be? You said, let's see, 7. Yeah, that's the 7th. That's a nice round number.
It is.
And that's the only place you'd hear it there. Wow, that's a nifty one.
I don't like it.
Yeah, a subharmonic like that. Usually a transmitter like that wouldn't be very good at transmitting at those frequencies, but again, you're a half mile away, and depending on their power, you really shouldn't be hearing it. Yeah, again, I would try one of those filters and see how that works for you.
Okay, might it be intermod?
I was thinking of that, but she says that there's a subharmonic relationship. If it would be intermod, it would be related to, you should hear, first of all, you'd probably hear 2 stations, unless the other one is a dead carrier. And she's getting a relationship between her internal, oscillators. Excuse me. This is, by the way, this is the Elecraft, you said?
Yes.
And it's the KX2?
Yep. And I'm a brand new owner of it, so I don't know that I know what I'm doing right. So
There's no reason to apologize. So hang on, I'm going to stop sharing here. Oops, I don't want to do that. I did not stop. There we go. I'm going to be looking at something here. I want to look at something real quick. While I'm looking for that, does anybody else have some questions?
Yeah. Does linear loading have the same effect as a coil? So like if on a dipole?
Yep. Okay. And it is so what you're doing is you're making the antenna basically one long coil. And yes, it does. It also reduces your radiation resistance. Are you still hearing me? Hello?
Yeah.
Oh, okay.
Yeah, thank you.
Yeah.
Sorry, I was nodding, but.
Would it help Heather if, I know she's on Oahu, and she said, I know she operates on a hill, and she's saying at about the same height as the transmitter.
Yeah.
She probably wants to get out to the northeast. I'm assuming maybe. And would it help for her to go down the hill and try and shield herself from the transmitter as opposed to being up, staring it in the eye?
It depends on their antenna pattern. Usually it's horizontal, yeah. So I'm not fine. I'm looking at the Elecraft, and it looks like it's a standard little baby.
So the other location I try to operate from is my condo, and it's in between where I usually like to on the hill and the transmitter, but it's also in line and pointed towards the transmitter and about the same height. So wherever I go, I have this problem.
Yeah. How are you powering the radio?
Internal battery.
So you're using the internal battery. Okay. Is the radio when you're using this on the antenna, is the radio grounded when you're doing it?
Not when I use the dipole on the hill, I guess.
Yeah.
I have had the radials out on it. I can still hear things.
Yeah. Yeah, it sounds like you may be encountering overload. That's a new one for me. And I could look into that. I'm going to note your name and everything and see what I can find.
Well, Buzz will appreciate this. It blocks out FT8, which is what I was trying to listen to see if the band was open.
Oh, that's unfortunate. Okay. Okay. That's a good one. The thing about it is that it's subharmonics. If it was intermod, you could get all kinds of different sources for it. You wouldn't necessarily get the subharmonics. So what, again, what frequencies do you normally, so you hear like, would you hear something on 80 meters?
I don't know.
Oh, what? Well, so you've heard it on 20.
I've
Where
heard it
else?
on 20, and then I divided 98.5 by like a bunch of numbers, and I painstakingly tuned the KX2 to those frequencies. And I've heard it on one of the other ones that I had the patience to tune to. I don't remember which one. Either divide by 4 or divide by 5, one of those.
Okay, so but it is definitely some harmonics.
Oh, it's definitely like I can hear it, and I have like another radio next, like I can verify it's the same music or whatever.
Right. And the interesting thing is that you're hearing it on AM, and that usually, yeah, there's some principles with the way FM works and everything like that. And every FM transmitter is also a little bit of AM associated with it. And it sounds like you're hearing the carrier actually being AM modulated a little bit. That's a new one. And by the way, just curious, is it fairly clear or is it distorted?
It's a little distorted, but definitely enough that I can.
It's intelligible.
Yeah, obviously, yeah. I caught the call sign. Well, I was so mad when I caught the call sign. I was like, no, that's what the noise is.
Yeah. Okay. Let's see if we can figure this out. And if anybody can suggest a low pass filter for Heather, that would be good. The other thing, your antenna is what again?
I've tried a couple of antennas. So 20 meter dipole. I've tried, I have a Hustler vertical. I've tried that. And I have like a vertical that goes with the KX2. I've tried that.
And they've all caused this?
Yes.
Okay. Just trying to think of how you could, yeah, we're gonna have to work on that one.
Okay, I'm sorry.
No. This is why you have a community like this. I think this is a challenge. I feel like Sherlock Holmes.
Okay,
so,
because I feel like most of the other condo hams up here don't operate from the condos. They go somewhere else. So they may not notice if this is a problem. I haven't heard. Most of them
But
don't do HF. In
you
the
might
combos.
try to, yes, you might actually chat with one and see if they've done, even if they just turn on their radio and listen in at their location and see if they're getting the same thing. And if it's a different radio and they're still hearing it, that may be telling, because it may be the transmitter, not you. But I'm gonna look up on them.
Okay.
Let's see what I can find out.
Just as an observation, would dropping a pad attenuator on that indicate whether it might be some of the other bands?
Overload, yeah. Yes. So does the KX2 have a front end attenuator?
Yeah, I think so. It has like a button.
Yes. I would turn those. Are you using the preamp?
If I use the preamp, yes, I hear it. If I don't use the preamp, I still hear it.
Okay. Try the attenuators. Turn up to maximum attenuation and see what you hear there. If you're still hearing it, now we're beginning to suspect it's coming from someplace else and it's not your radio or overload.
Okay.
All right. See if it
Okay.
goes away with that. Because that's going to have the same effect as filtering. You might not hear the signal as well. You know, obviously it's going to attenuate everybody. But if we suddenly see it go away, you're going to have, you might have a serious problem there with just overload, and filtering would help that. I'm going to look that, by the way, I'm going to try and look that up while you're online here. Hold on a second. So you said it's Island Radio?
98.5. Someone dropped the call sign in the chat.
Oh, they did? I didn't see it. What was it?
KDNN.
KVNN?
Kilo Delta November November.
Thank you. FM. Okay. Oh, it's a reggae station. Ooh.
Yes, it definitely is. It comes through in the CW band too, just like doo 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 doo.
Yeah. Oh, and they have Stupid Joke Fridays. Oh, how nice. Anyway, I'm looking it up here in the FCC and see what they've got. Ooh, 51 kilowatts. Okay. Did I lose everybody? Did I lose?
Nope.
Oh, you're there? Okay.
Still here.
Yeah, everybody's looking it up because the FCC database is melting. Anyway, there it is. Okay, Honolulu technical data, blah, blah, blah. Let's see, it's non-directional. So it's 51 kilowatts. Unfortunately, they won't tell me what the transmitter is. It's been on the air since '88. Yeah, I'll have to look at it. All right. Anybody else? Okay. Buzz, it seems like I've exhausted everybody. I see some people have checked out, so I'll turn it back to you.
Jay, thank you so much. Wonderful job. I am sure everybody pulled something from this. I'm not sure anyone pulled everything from it. And I want to thank you for taking your time and energy to come and do this. So if there's no final questions, I'll thank you. We hit 49 participants at the height, and that's a great turnout. Any other questions or comments? Okay, thanks for coming, and I'll see you at brunch on Monday, Jay.
Okay, 73s, everybody. And if you have any other questions, you think of something, I'm not in QRZ. I am in QRZ.com, but it doesn't have the email on it. You can always send something to Buzz, and he can forward it on to me. Okay. All right.
Thank you very much.
Thank you.
Thanks again.
Thanks, Jay.